Welcome to all of you. Now we discuss about Bendixson's negative criteria and Dulac's criteria on biomathematics. First, we study Bendixson's non-existence criterion or Bendixson's negative criterion or Bendixson-Dulac theorem for non-existence of closed path. Let D be a domain in the xy plane. Consider the autonomous system dx dt equal to pxy, dy dt equal to qxy, where p and q have continuous first order partial derivatives in the domain D. Suppose del p del x plus del q del y, actually del p del x plus del q del y, actually the uh, divergence of this vector field has the same sign throughout the domain D, then the autonomous system 1 has no closed path in the domain D. So del p del x plus del q del y has the same sign. Either it is positive throughout D or it is negative throughout D. Then system 1 has no closed path, no periodic path in the domain D. Here this in a planar system, this F, the system x, y and x equals to small x small y. This furthermore F, where F is a continuous function, first order partial derivative in the region E, then del x del small x plus del capital Y del small y, that is the divergence of the vector field F. This is the vector field F, is the capital X capital Y. This then is always of the same sign but not identically zero, then there is no periodic solution in the region E of the planar system. Proof of this theorem: let C be a closed curve in the domain D. Also let R be the region bounded by the closed curve C. Then, applying Green's theorem in this plane, we have closed integration on the curve C, p dy minus q dx. This equals to double integration is the surface integration over R del p del x plus del q del y into ds. ds is the elementary area in the over the region R, where the this line integral is taken in the positive sense. Let small x equals to ft and small y equal to gt be an arbitrary solution of the system 1, autonomous system 1, defining the curve C parametrically. So this x equals to ft and y equal to gt represents the curve C, the trajectory C, the C of the system 1 parametrically. Let capital T denote the period of this solution. Then by 1 dx equal to p dy equal to q, we get ddt of ft equal to p of ft gt and ddt of gt equal to q of ft gt. We put here x equals to ft and y equal to gt. along the curve C. Also, the closed interval integration over the closed interval C, p dy minus q dx, this equal to integration over t equal to 0 to t equal to capital T, this time period of this. Then this equals to p into g dg dt and minus q into df dt into dt. So this dg dt equals to q, put here q, and this df dt equal to p. So pq minus qp into dt, obviously this equals to 0. Hence, this closed integration over C this equal to 0. Also, we have this closed integration equals to the double integration over R is this. So obviously, this equals to 0. This double integration is equal to 0. Hence, this double integration over R del p dx plus del q del y into ds equals to 0. But this double integral can only be 0 if del p dx plus del q del y changes sign over R. But it is wrong, because we assume that del p del x plus del q del y has the same sign throughout this region. So C, trajectory C is not a closed path of the system 1. Hence, the system 1 possesses no closed path in the domain D. This completes the Bendixson negative criterion, that is Bendixson's non-existence criterion, that is Bendixson Dulac theorem. Now we consider some example by this theorem, application of this theorem, so that the system dx equal to 2x plus y plus x cube dy dt equal to 3x minus y plus y cube has no limit cycles. Let p equal to this 2x plus y plus x cube and q equal to 3x minus y plus y cube. Then del p del x plus del q del y equals to 3x square plus y square common plus 1. Since this expression is positive throughout every domain D in the xy plane, because x square plus y square is always positive, so this quantity is always positive throughout the domain D. The above system has no closed path in any such domain by Bendixson negative criteria. Hence, the given system has no limit cycle, obviously, no closed path, obviously, and no limit cycles. Next example, using Bendixson's negative criterion, so that the following system has no closed orbit inside the circle with center 0, 0 and radius 1 by root 2. System is this given dx dt equals to this and dy equal to this. Let fxy equals to minus y plus x into this and gxy equal to x plus y into this. Then del f del x equal to this and del g del y equal to this. Then del f del x plus del g del y equal to 4 into x square plus y square minus half. And this quantity is less than 0 if x square plus y square less than half. So del f del x plus del g del y has the same sign here, negative sign, inside the circle x square plus y square equal to half. So in this region, del f del x del g del x has the same sign. Actually, they are negative. So also this region is a simply connected region in R2. Hence, by Bendixson's negative criterion, the given system has no closed path inside the circle x square plus y square equal to half. Note that outside of the circle x square plus y square equal to half, del f del x plus del g del y has the same sign, positive here. Obviously, outside, that is when this is greater than 0, positive, when x square plus y square is greater than half. So this quantity is positive, del x del y del positive outside the circle. But this outside region of this circle is not a simply connected region, and so we cannot apply Bendixson's negative criteria on this region. Actually, for this system, this dx dt equal to this and dy dt equal to this, we get an unstable limit cycle x square plus y square equal to 1. This, so this in anti-clockwise direction orientation, and this is the from to away from this circle. So this is the unstable limit cycle of this. Now, what is simply connected domain? Simply connected domain is a path connected domain where one can continuously shrink in any simple closed curve into a point while remaining in the domain. So this region is simply connected domain because we can continuously shrink any curve, closed curve in this region into a point without mm, leaving this region. But this region is not simply connected. This shaded region is simply connected because when any closed curve in this region, we cannot shrink this closed curve into a point without leaving this region. Uh, so this is not simply connected region. Next example, the system dx dt equal to py plus x to the power n dy dt equal to qx has no closed orbit if n is even, odd, either even or odd, none of this. Here py and qx are first order continuously differentiable function and n is a natural number. Actual answer is set 2, odd. When n is odd, has no limit, no closed orbit. Let fxy equals to py plus x to the power n and gxy equal to qx. Then del f del x plus del g del y equal to n into x to the power n minus 1, because del f del x is p function of y, so this is 0, and del g del y, this is function of x qx, so this is also 0. So n x to the power n minus 1. If n is odd natural number, suppose n equal to 5, so 5 minus 1 is 4, so x to the power 4 is always positive, always positive. So fx plus gy has same sign here, positive, if n is odd. Then Bendixson's negative criterion or the given system has no closed orbit if n is odd. Next example, show that the following system has no closed orbit: dx dt equal to y, dy dt equal to ax plus by minus x square y minus x cube. B is negative. Let fxy equal to y and gxy equal to ax plus by minus x square y minus x cube. Then del f del x plus del g del y equal to this 0, this b minus 4x square. Obviously, this 4x square minus is negative, and if b is negative, also given that b is negative, so obviously this is negative. B minus 4x square is negative. So Bendixson's negative criterion, the system has no periodic orbit closed path if b is less than 0. Next example, so the system dx dt equal to this, dy dt equal to this has no closed orbit in the first quadrant in the xy plane. And let fxy equal to x into 2 minus 3x minus y, gxy equal to y, 4x minus 4x square minus 3, del f del x equal to this, del g del y equal to this, del f del x plus del g del y equal to minus 4x square minus 2x minus y minus 1 is 0. Here, first quadrant means x greater than 0 and y greater than 0. So obviously, this minus 4x square minus 2x minus y minus 1 obviously less than 0. Hence, fx plus gy has the same sign, here actually negative, in the first quadrant. Then by Bendixson's negative criterion, the given system has no closed orbit in the first quadrant. Also, first quadrant, this is also simply connected region over R2. Next example, so that the system x dot dx dt equal to this minus y plus x square plus y square minus 2x minus 3, y dot, that is dy dt equal to x plus y, x square plus y square minus 2x minus 3, has no closed orbit inside the circle x minus 3 by 4 whole square plus y square equal to 33 by 16. Let fxy equal to this and gy equal to this. Then del f del x equals to this, del g del y equal to this. Then del f del x plus del g del y equal to this. And after rearranging this, 4 into bracket x minus 3 by 4 whole square plus y square minus 33 by 16. Obviously, this quantity is negative when x square minus 3 by 4 whole square plus y square is less than 33 by 16. Hence, this fx plus gy has the same sign, actually negative sign here inside the circular region. Obviously, this inside the circular region is a simply connected region in R2. Then by Bendixson's negative criterion, the given system has no closed orbit inside that circle. Next, state Dulac's criterion for periodic solutions. Consider the autonomous nonlinear system dx dt equal to pxy, dy dt equal to pxy. P and Q have continuous first order partial derivatives in a simply connected region D of R2. If there exists a real valued continuously differentiable function Bxy called Dulac function or weight function in the domain D such that del x of Bp plus del y of Bq has the same sign, either positive or negative, throughout the region D, then the system has no closed orbits lying entirely in D. This is the Dulac's criterion for periodic solution. Obviously, this when b equals to 1, this Dulac function, that is what weight function is equal to 1, obviously this Dulac's criteria uh, is the Bendixson's negative criteria. Example, using Dulac's criterion, so that the system dx dt equal to this, dy dt equal to this has no closed orbit in the first quadrant. Here, A is greater than 0 and D is greater than 0. 2022. Let D is the set of all those order pair xy belongs to R2 such that x greater than 0 and y greater than 0. Actually, D is the first quadrant in R2 xy plane. Obviously, D is just simply connected region in R2. Let fxy equals to x bracket of alpha minus ax minus by and gxy equal to y into bracket beta minus cx minus dy. And consider Dulac function bxy equal to 1 by xy. It is very important to choose in such a way that this Dulac function bxy equal to 1 by xy. Remember this. Then del x of ab plus del y of gb. This, so obviously del x of f into b, f equals to x into alpha minus ax minus by, and into b means 1 by xy plus del y of g, y into beta minus cx minus dy, into b means 1 by xy. So cancel this, and after partial derivative with respect to x and with respect to y, we get minus common a by y plus d by x. Obviously, a and d is positive. Given that a and d is positive, obviously this quantity is negative because x and y lies in the first quadrant. So del x of fb plus del y of gb has the same sign here, negative sign in the first quadrant. Then by Dulac's criterion, the given system has no closed orbit in the first quadrant. Next example, using Dulac's criterion, show that dx dt equals to minus y plus x square minus xy, dy dt equal to x plus xy has no closed orbit for all x greater than 0, y greater than 0, and taking the weight function, that is Dulac function bxy equal to minus 1 by 1 plus x into 1 plus y whole cube. Consider D lies in the first quadrant. D is the first quadrant of xy plane. So we take this xy belongs to R2 and x greater than 0, y greater than 0. Obviously, D is simply connected region in R2, and let fxy equals to this minus y plus x square plus minus xy, and gxy equal to x plus xy. Then b into f, here b is this minus 1 by 1 plus x 1 plus y whole cube. So multiplying this b into f and this minus, so taking common minus from uh, numerator, we get y into 1 plus x minus x square whole divided by this. Obviously, y into 1 plus x divided by this, so cancel 1 plus x, so we get y by 1 plus y whole cube minus x square by 1 plus x 1 plus y whole cube. Then del x of bf, the del x of bf, so obviously this quantity is free from x, so this is del x of bf. So from this term we get 0, and from this term 1 by 1 plus y whole cube, this constant term minus of this, and this 1 plus x into 2x minus this square of this, so we get this quantity. Similarly, we get bg, b into g equal to this, and del of bg equal to this. Then adding these, del x of bf, del x of bf plus del y of bg equal to this. So after simplification, we get x square by 1 plus x whole square 1 plus y whole cube. Obviously, this quantity is greater than 0 because xy lies in the first quadrant. XY point lies in the first quadrant, belongs to D. Then by Dulac's criterion, as del X of BA plus del Y of BG has the same sign in, in the simply connected region D, then the given system has no closed orbit in the first quadrant. No closed orbit in the first quadrant. So you can uh, try this H-plane plotter dx dt equal to minus y plus x square, sorry, x square minus x into y, minus y plus x square minus x into y, and dy dt equal to x plus x into y. So clearly, by from the phase portrait, there is no closed orbit in the first quadrant. In the first quadrant, there is no closed orbit in the first quadrant. This completes the lecture. Thank you for watching this video.